Well, hello and welcome to, I guess, another regular science meeting for the Maston Public Library. Joy is not here to introduce me, so I'm introducing myself. Today I thought I would talk about black holes, which is actually quite relevant because this year one of the Nobel Prize in Physics was awarded to three people for work related to black holes, I guess I would say. And it was split into two groups, one for Roger Penrose, who actually worked on theoretical stuff, and then the other one for, and I'm gonna screw up these names, Reinhard, Genzel, and Andrea Ghez, who have been doing a lot of great work on proving that there are black holes, and specifically in our galaxy. So I thought I'd start with, what do we mean by a black hole? What is a black hole? And there's actually a long history of what a black hole is and what we understand about them. It all goes back to the early 1900s when Albert Einstein came up with his theory of relativity. And he started with the special relativity that looked at how things move relative to each other. And then he developed the general theory of relativity, which is about gravity. And this was about 1909 or so. The radical thing about Einstein's theory of gravity is that Newton said that gravity was a force. The moon pulls on the earth pulls on the moon. The reason an apple falls is because there's a force of gravity acting on it. And that was so accurate that it was basically considered to be written in stone. That everything is forces. You have forces that cause things to move, they cause them to speed up and slow down. So everything has to be forces. And Einstein's theory of relativity said something very different. Einstein said that gravity is not a force, as strange as that is, that what's actually going on is that when you have a large mass like Earth, it actually warps space around it. Space isn't flat, it's curved around this mass, so that if you move something in a straight line, it actually changes direction because space itself is curved. This is one of those weird things that it was so bizarre at the time that when Einstein gained recognition for it, I think the New York Times said that probably only 5 people understand what relativity is. So it's this very weird theory. It was completely revolutionary, but when they started doing experiments, it actually worked. So one of the first ones was Arthur Eddington, who looked at how light would behave near the sun. So he looked at the sun during a total eclipse, and he saw that the positions of stars seem to move farther away from the sun than they actually should be. And the reason was because light was bending around the sun. So if you look at like a lens, the light bending around the sun makes the star appear farther away than it actually is. So it's actually here, but because the light kind of comes and then bends, we look at it in a straight line, we see it over here, we see it farther away. So seeing that shift in starlight was one of the predictions of Einstein's theory of relativity, and it showed that it was right. Well, as soon as this kind of started, as soon as people started realizing that Einstein's theory actually works, and it wasn't just light, it was also things like the motion of the planets. There's little weirdness in the motion of Mercury, for example, and that agreed with relativity. So relativity agreed with Mercury, it agreed with the bending of light, it agreed with other things, and people started saying, okay, we really have to understand this theory. And again, this was early in the 1900s. So during World War I, there was a German grenadier. So this is a guy who calculated out all the calculations for firing a gun, like a cannon. And in his spare time, he worked on Einstein's equations. His name was Schwarzschild, and he came up with this really weird solution. So he came up with a solution to Einstein's equation that described what the structure of space and time was around a mass. And what he found was that if the mass was dense enough, if it was small enough and massive enough, then what would happen is that space would kind of collapse in on itself. And not even light would be able to escape it. So that basically, light bends in a gravitational field, it's deflected. Well, if you have a strong enough gravitational field, then light can't even get out of this hole. And so there was like this hole in space that no light could escape. So it would be black, it would be a black hole. And so this was one of the early predictions of relativity. Well, basically what you're saying is that no matter how much energy you have, no matter how fast you move, you can't get out of this black hole. What Schwarzschild found was that if you have this really dense object, then basically there is a point of no return that he called the event horizon. And that meant that if you cross that event horizon, you aren't getting out, period. I mean, there's literally no physical way for you to get out. This led to a lot of theoretical problems. And at the time when it was sense. It would be like there would be one direction that you could move in space, but not the other. It would be like you could move left, but not right. That if you took a step to the left, it would be physically impossible for you to take a step to the right, which made absolutely no sense. How could space possibly fold in on itself and trap something, And so this was one of those things that was really fiercely debated. And it was one of those things that, like, black holes were actually a joke. The idea that, oh yeah, right, there's this thing that falls into this black hole. Because for some reason the name stuck, it's neither black nor a hole, but the idea that you would have something that would completely trap anything that crossed into it, this kind of cosmic Roche motel, didn't make any sense. And there was another aspect about it, is that when other people looked at this, what they found was that suppose you had something that was heavy enough to crush itself. So like a really large dead star that would collapse in and collapse in. Well, what they found was when they did all the math, if you collapse into a black hole, you can never go outward from where you are. So if you have a mass that collapses into a black hole, then it can't expand or explode or do anything. All it can do is collapse and collapse and collapse and collapse, to the point that if you keep following it collapsing and collapsing and collapsing, all of the matter of this black hole collapses down to the size of an atom, and then keeps collapsing to it's the size of an electron. Then it keeps collapsing so that it's smaller than anything, and you would get all of the matter of this black hole would collapse and collapse to a point of zero volume. And they called that the singularity. And you say, okay, wait a minute, wait. Okay, so Einstein's theory predicts that if you have enough mass, space will fold on itself and the matter will collapse to a singular point with no volume, and all the laws of physics will break down. I'm calling nonsense on this. And a lot of physicists did. It didn't make any sense. The math broke down, the logic broke down. I was like, this black holes surely can't exist. And so it was initially, when it was studied, it's like, that's a nice mathematical trick. But a large part of astronomers would say, yeah, there's got to be something wrong with the theory of relativity. Black holes don't exist, and let's move on. As time went on, as we started gathering more things, we started to find things that were really kind of odd. So for example, we would find within galaxies these really bright radio sources. I mean, extremely bright radio sources, very far away. And you calculate out, like, how could you produce that type of energy? And the numbers started coming up towards black holes. There were objects that were called quasars, and they stand for quasi-stellar objects. They're objects that look like bright radio stars, but they're so far away, they might as well look like a point. We didn't know how could they possibly be powered, because they had to be incredibly powerful radio sources. Well, black holes were a possibility. So they started, and so with quasars and other objects, astronomers started looking at what could possibly be a black hole. And one of the things that they found was that quasars are these bright objects, and they tend to be in the centers of galaxies. Well, we're in a galaxy, so maybe in the center of our galaxy is a black hole. The problem is, how do you prove it? And so if you look at the Nobel Prize, Roger Penrose won the Nobel Prize. He got half the Nobel Prize this year because he actually showed that black holes could form. So one of the weird things about black holes was that if you have gravity pulling on you, Einstein's theory of relativity says that the stronger the gravity, the more time slows down. So some people said, well, that means you can't have black holes because the time would slow down and slow down and slow down. Nothing could ever collapse past the event horizon because of all this wibbly wobbly time stuff. And Penrose showed that no, in fact, if you have enough mass in a small enough volume, gravity will in fact squeeze it into a black hole. So that theoretically, if you get enough mass in a tight enough space, you get a black hole. So that's where his half of the Nobel Prize comes from, because he showed that Einstein's theory proves that black holes are inevitable. The other two got the other half of the Nobel Prize because they proved that a black hole exists. And it's actually kind of an interesting story because black holes can come in different ways. The original idea of a black hole was a star that collapses. Star runs out of fuel. It's so large that gravity squeezes it in on itself. But when we observed quasars, we would see black holes, or what looked like something powered by black holes, that would have to be extremely massive. Not just the mass of a star, but the mass of millions or billions of a star. The mass of basically a small galaxy just squeezed into the center in a way that could be powerful enough to create this kind of bright radio light. So a group of astronomers decided, let's see if there's a black hole in the center of our galaxy. And the problem is that our galaxy is basically this disk. And it's this disk with this little bulge towards the center. And we're about 30,000 light years from the center. And so if you look directly towards the center of our Milky Way galaxy, towards Sagittarius, what you see is a bunch of dust. Because you're looking down, basically down the barrel of a galaxy where there are stars and dust and everything else. And so you can't see the center of our galaxy. There's just so much clutter in the way. So what these astronomers did is, rather than looking at it in visible light, they decided to look at it in radio light. And the reason why that's useful is that radio, just like you can pick up a radio station in your house, even though it's surrounded by walls, you can see radio through gas and dust. And the reason is because radio has a much longer wavelength, and so it penetrates through matter much more easily. That's why you can get radio in your house through the walls. That's why you can pick up a cell phone signal through the walls. That's why we can see through the gas and dust. So they looked at radial light coming from the center of the Milky Way. And what they found was there are, near the center of our galaxy, several very bright, fairly large stars. Now you think of a star as giving off visible light, but stars actually give off an entire spectrum of light. And so these large stars weren't just giving visible light that was all blocked by the gas and dust. They were also giving off radial light. Our sun gives off radial light, so we can actually see the sun in radio wavelengths. So they could see these points of light in radio wavelengths, that light coming through all the gas and dust. They could see where these stars were. So what they did is they pointed towards the center of the galaxy and watched these stars year after year after year. So they've been doing this for about 40 years now. What you see is if you watch these stars, they move over time. And they appear to be orbiting something. And you can actually watch them orbit the center of our galaxy. So over decades, some of them have orbits of like 12 years or so, but you can calculate, if you watch them year after year, you can plot out the motion of their orbit. Now, the thing that's really cool about this is that the orbit of any body around a mass depends upon a couple of things. It depends upon how far away it is from the mass. And it also depends upon what the mass of the object it's orbiting is. So, for example, we can watch one star orbit another star, and if we figure out what that orbit is, we can actually calculate what the mass of those two stars are. Because we know how fast it's orbiting, we know how far away they are, we can do all of this. So you do this with the stars in the center of the galaxy, and what you find is they're orbiting this object that has to have a mass of at least, it's about 4.1 million suns. So it's 4.1 million solar masses. And if you then look at how close these stars are actually orbiting, that 4.1 million solar masses has to be within the size of our solar system. It can't be really big. It's not spread out. It's very, very concentrated at some small region. So if you do the math, you find out that that much mass, 4 million suns in a mass smaller than our solar system, has to be a black hole. And so the second part of the Nobel Prize was to show that, in fact, there is a supermassive black hole, what we call a supermassive black hole, in the center of our galaxy. It's just about 30,000 light years away from us. And it's sitting in the center of the Milky Way. And so that was one of the real conclusive proofs that black holes exist. Now, even with this evidence, and it wasn't just the Milky Way, we've also seen it in other galaxies, even with the evidence of quasars and these stars moving around this dense black hole object, there were still some scientists that would say, well, I'll grant you that it's really dense, but I'm not going to say that it's actually a black hole. I'm not convinced that a black hole can actually fold space around it and collapse into a singularity. I'm not buying it. So most astronomers would look at all the evidence and say, yeah, sure, they're black holes. We have to admit that black holes exist. But there were still some astronomers that would say, I'm not buying it. I'm still calling shenanigans here, And so a couple of years ago, there was a project to actually take this one step further. And that was to actually observe a black hole directly. So this was a big deal because most of the evidence that we've had for years, say probably for the past 10 or 15 years, the evidence that we've had for black holes has been indirect. So if you look at the motion of stars in the center of our galaxy, they very clearly orbit exactly the way Einstein says they should move around a black hole. And we know that whatever is in the center of our galaxy has to be really, really dense. But if you look at the data, you can't prove that it actually has to be the size of a black hole. Maybe it's just a little bit bigger than a black hole for reasons we don't understand. So you couldn't quite prove it. When you look at quasars, you can say, look, these things have to be powered by really intense gravity. The gravity has to be at least this intense. But then someone would say, well, but it comes from a region outside the event horizon, so it could still be something that's really dense and not a black hole. So there were still some people that were holding out this idea that, well, maybe it's not a black hole. So a few years ago, there was a radio astronomy project that decided to try and look at a direct image of a black hole. And what they did was, in order to see something that small, it's basically the equivalent of taking a golf ball, putting it on the moon, and being able to see the perimeter of the golf ball. That's how sharp your picture has to be if you want to see a supermassive black hole. Well, to do that with radio astronomy, the sharpness of your image depends upon the size of your telescope relative to the wavelength that you're looking at. So this is why larger telescopes have sharper images than small telescopes. If you have a little hobby telescope that's 2 inches wide, you're not going to see a lot of sharp images. If you have one that's 15 inches wide, you'll see some sharp images. So if you do this with radio light and you want to see something the size of a golf ball, you have to have a radio telescope the size of Earth. Of course, we can't make a radio telescope the size of Earth. So what they did was they used a process known as interferometry. The thing about radio is that because light takes time to reach you, you can actually have a whole bunch of little antennas spaced apart. And as the light comes across, it'll hit one antenna and then another one and then another one. And if you check the timing on that, you can actually combine those signals to create this kind of virtual telescope, as if you had a little block of the telescope in different spots. And so it takes supercomputers to combine all the data, but you can do this. So what this group decided to do is they're going to take radio observatories from all across the world, and they're all going to look at this galaxy called M87. It's a spiral galaxy very similar to our galaxy, but it has a very clear view of the center. So they got these radio telescopes from all over the world, and they watched it for months and months and a year and a half and gathered all this data. They gathered so much data, they can't transfer it over the internet. So they actually had to store it on hard drives and fly it to a computer that could process all of this data. And so they did this. And what they got was, by creating an image, a telescope the size of the Earth, they got this little dark image with a halo around it that was the light bending just over the event horizon. So they could find where the glow of light just around the event horizon was sitting there in the center of this galaxy called M87, where you could see the black hole. You can't see the black hole directly, but you can see the light that's bent around it. So they did that, and the size of that shadow, the shadow of the black hole, was exactly the size of a black hole given its mass. So it's a billion suns, and they could see this in another galaxy from this shadow of the black hole. And the only thing that can be is a black hole. The shadow is so small, it can't be bigger than the event horizon. So they've proven that these black holes exist. So this is what got the Nobel Prize, was this whole series of things leading up to proving that black holes actually exist. Most galaxies actually have a black hole in them. And so our galaxy has a supermassive black hole, and other galaxies have black holes. We know now that not only do black holes exist, but they can span a whole bunch of sizes. Some of them are the mass of 10 stars, like 10 suns. But the ones in the centers of galaxies can be millions or billions of suns in mass. They can have so much mass that they could swallow our solar system whole. As the event horizon is bigger than that. So we know that they exist. We know that they're common. We know that they're spread throughout the universe. We know that they are the power behind quasars. But we still don't know what exactly happens inside of them. And this is kind of the next big question in astronomy when it comes to black holes. Einstein's theory, every time we test it, proves right again and again and again. All the strange predictions that Einstein has made about how it warps space and time, how black holes exist, how space can fold in on itself, all of that is true. We've shown that it's true. But Einstein's theory about black holes still predicts that all of the matter will compress into a singularity, where all the laws of physics break down. Einstein's theory is still incompatible with things like the theory of atoms, what we call quantum physics. Quantum physics works really well. It's why we have computers and lasers and all these wonderful, cool things. But the quantum theory disagrees with Einstein's theory. So we're kind of at this real big problem. We know from material science and computers and all of that quantum physics works. It works as much as we can prove it. On the other hand, in astronomy, we know that relativity works, and it works as much as we can prove it. And if you try and put the two together, they don't fit. Quantum theory and relativity contradict each other, because quantum theory says you can't have a singularity, and general relativity says you have to have a singularity. So something's wrong. Now, there's a hope that those two can somehow be combined into something we would call quantum relativity, or more broadly, the theory of everything, if you really want to be egotistical about it. But this idea of how do you combine quantum theory and relativity, we don't know. We really don't know. So we've won the Nobel Prize for black holes, we've won the Nobel Prize for quantum physics, and now we're at a mystery. And that is the next step in physics and astronomy, is trying to figure out how do we fit those two together? And we don't know. All we know is that both of them are absolutely true to the limit of what we can observe so far. And we also know that they completely contradict each other. So we've had a Nobel Prize for black holes, and it raises a whole bunch of other problems. And that's currently where we are. So, any questions on that?
No, I don't think so.
Okay.
You explain it really well.
Yes, as always.
I try.
If I understand it, you know it has to be explained well.
Yeah, it's an interesting thing, because quantum physics was one of those things that we could prove by making things in a lab. I have a phone. Congratulations, quantum physics works. But at the same time, if I want to find my local Starbucks, I can use my GPS and Google Maps, which is using general relativity. The satellites have to actually account for the dilation of time in order to work. So this proves that quantum physics is right and general relativity is right, and they disagree.
Oh, dear. That's life.
Wow.
That's life, yes. So we have to get used to the unknowns.
Well, know.
So what's your best guess? When do you think they'll have an answer?
You know, I think it could be 5 years, it could be 500 years. Honestly, I think what we will need is not just another Einstein, but we'll probably need about 10 of them. You know, to figure out how this works, because they're so contradictory and they're so problematic for each other. From the very ground of where these theories start, they make assumptions about the universe that cannot both be true. You start with, it's like you start with one idea and you build it up into this great theory that actually works. And then you say, okay, all of that's nonsense, let's do this, and build it up another great theory that actually works. And nobody on the planet is smart enough to figure out how those two things work together. So we need lots of smart children to grow up into smart scientist adults and tell us what the problem is. And I still probably won't understand it.
So even with the super smart computers we have, we can't.
You know, that's kind of an interesting thing, is that, you know, could computers solve the problem for us?
Yeah.
And I don't think they can. Computers are really great at gathering data, and they're really great at analyzing things. But when we talk about a scientific theory isn't just what's true. It's a way for us to understand what's true. So it has to be presented within a human context. It has to be, in some sense, a story told by humans to connect us to what's really going on. And so it's going to take people to give us a theory that we can understand, you know, because we could have the computer that says, you know, if A happens, B happens. Okay, why? If A happens, B happens. Okay, that's true. But why does it work? You need some type of theory, some type of story that connects it into something that we can understand.
Okay.
So I think it's going to be people that are going to solve this, not computers.
Okay.
I hope so.
Okay.
Yep.
Great.
If there aren't any other questions, I guess I will stop it here. I think Stacy is thinking about another one in December, looking at like the different colors of the moon and why sunsets are red and things like that. So stay posted to her. She'll present where everything is. I think we're still working that out, but
Great.
that's
We'll
the
do that.
idea. So
Looking
other
forward
than
to it.
that, thanks for coming to the science lecture for Maston Public Library, and look for more in the future.
You bet.
Thank you, Brian.
Okay,
Bye.
Bye.
bye.